It's a pleasure to be here. Thank you, Ed, for inviting me, and thanks for all the organizers for this great opportunity here. Okay, so I'm going to start by describing to you. Why is this not working? Describing to you the main hypothesis that I'll be promoting here today, which I call the lasting primacy. And the idea here is that our brains, do a quick first pass of rudimentary information to determine our impressions, guide our predictions, and shape our perceptions. So, in other words, the idea here is that what we extract very early from a situation, from an image, from a sound, from whatever stimulus we're facing, the earliest information is what kind of flavors our entire interactions with this stimulus, our impressions and predictions, etc. So to go back for a second, I'll just tell you that my lab traditionally has been studying visual cognition. Ed and I went to graduate school together. I started before, so you can see I'm older, but we had a lot of great time together. And what I learned from Ed was primarily a musical appreciation, but we also got to do a lot of experiments on this. And since then, my lab has been focusing mostly, but not only, on visual cognition, understanding how is it that the brain understands visual information around us. And the more you think about it, textbooks, etc., you realize that there is an artificial boundary in the way they teach us about the distinction between perception and cognition. So perception, and there are different courses, different books, different careers, but basically the brain doesn't care about this. There's no line in the brain that says perception ends here and cognition starts here. So the brain works together. Cognition and perception are intermingled and work in tandem just to reach the goal. So perception, even if it means analyzing the low-level features, the physical features of the stimulus, and cognition is the higher level, executive control, attention, etc. We see, and I will show some evidence, that the brain actually uses both ends all the time. And I think even a simple example shows you that we don't only use perception when we look at something new, but rather there's this type of what we call top-down influences, information to predict what's coming next in this image. So we start to go about it with modifying the question, just taking a step back and thinking about what is it that the brain does with a stimulus. Okay, so traditionally, again, we've been thinking about the brain as looking at something and asking the question of what is this? You see something and you ask, what is this? And the more we thought and the more we studied, we realized that the more accurate question to think that the brain is asking is, what is it? What is this like? So rather than trying to figure out from the bottom up everything we encounter, we ask, what is this like? We try to connect things with memory, with things that are familiar to us as quickly as possible. So we do these analogies between input and memory to create a connection to knowledge that we already have through experience, and by this be able to generate predictions. So I can just show you two informal demonstrations, and I think none of you have seen me give this talk before. So for all of you guys, I bet these two stimuli are new. And if I have you look at this object that you've never seen before, and not only that you've never seen before, it's not a typical exemplar of its category. But I think all of you, at least most, but I bet all of you know what this object is, right? Okay. And not only that you know what this object is, I even ask you, what is this collection of pixels here? There's hardly any information here. And all of you know exactly what it is. You can imagine it in different situations. You know it in different contexts. And it's pretty amazing that our brain can look at a collection of pixels that we've never seen before, and we already have so much knowledge about what this object does, what is it used for, how much it costs approximately, how much it weighs approximately. You can imagine it in different situations. So I think this is pretty amazing. It's less desirable maybe when we do it with our interactions with people. We look at somebody that we've never seen before, and not only that we can say if this person is attractive or not, we can say that if he's even, I don't know, if he's a Mac person or a PC person. I mean, we can really go high level with our predictions, even though we don't really have real information. So even with human interactions, and I will be talking about this just a little bit. But basically, the very simple framework with which I'm looking at things here is that when we look at something new, and unfortunately, it's really rare for us to see something that's really, really new. When I said the brain is asking, what is this like? There's usually an answer. Usually, when you look at something, it's like something else, okay? So you connect it to something that is, most similar to this new input, and the moment you make this analogy, this connection, you gain access to this ocean of associations in your brain that have been accumulated with your experience, and this activation of association is really predictions, what to expect from this stimulus that you're facing. So I'll run through a few studies without technical details, but just to kind of build the story. And starting with a study, my first MRI study when I was a postdoc, about just object recognition and what happens in the brain when we recognize what this object is. Okay, so I'm sure that you're all familiar, even the people who don't do imaging are familiar with this presentation, but just in case, I'll say this is the front of the brain, this is the back of the brain, and this is the temporal lobe, and what you see here is inflated brain, so you can see the soul side, they're also exposed, and these are kind of proxies to real activation. This is a bold fMRI signal. And we found that this region of the brain shows more activation when we recognize an object. When we know what an object is, this area of the cortex is more active. That's nice, and this was new back then, but now it's old news. But the reason I bring this study here is that we also got this prefrontal activation, this high-level activation in just simple object recognition experiment. And it was kind of puzzling for us because, again, as students, we studied that perception is in the primary cortex, in the primary cortex and just visual cortex, but in sensory cortex. Why is this high-level prefrontal cortex area be active when we talk about seemingly a perceptual task? So this kind of caught our attention. We started entertaining different models, and the two primary ones that I wanted to compare were one is the traditional one. Why? Again, the question is, why is the prefrontal cortex active in an object recognition task? So the traditional view is that everything is bottom-up. Well, it used to be the traditional one. I would say by now that people have realized that it's not the case anymore. But here, the idea here is that information from the visual world enters our primary visual cortex in the back of our brain, and then it propagates along the ventral pathway. There are other pathways, but this is the form pathway. And it analyzes systematically all the features, line, orientations, colors, contrast, etc., until it understands, the cortex here understands, oh, this is an umbrella. Let's share this information with a higher level cortex to do this executive stuff with this knowledge. So this is arbitrary boundary I mentioned between perception and cognition would be about here. The alternative that captivated my imagination much better was that this thing actually happens in parallel, that the prefrontal activation signifies some sort of anticipatory process, some kind of expectations about what the object might be, and it's not just waiting to be activated with a final outcome, but rather sends down some predictions and some guesses about what the object might be to facilitate this process. And how is such facilitation could be accomplished? So there are special frequencies in the visual, just like in auditory domain, and low special frequencies convey the general blobs and general aspect ratios and the big details, the coarse but important details about the visual information. And there's the other end, which is the high special frequencies that conveys the details, right? The fine details. And by the way, this girl here is here in the audience. It's my daughter, and she's 15 today. So, so I'm happy that she could join here as well. So the idea here is that low spatial frequencies, if I just show the low spatial frequencies of images, so I think all of you guys will know that this is a giraffe, right? I'm not planting an answer here, but let me hear some guesses about what do you think this blob is, what this object might be. Gun, drill. You guys know my papers? Okay, what else? Hair dryer, nice. You all get an A. Okay, so the idea here is that a blurred image seems highly coarse and highly uninformative, and yet it limits the set of possibilities that we can consider. So instead of looking at something and going through the library of the tens of thousands of objects that we know that we store in memory, this type of information, even though it's very, very coarse, can already limit the set of possibilities that we need to consider. So that's a huge computational saving right here. So the idea here is that in parallel to, and I don't know if I said it, but anyway, this type of low spatial frequency information is available in the cortex earlier than the high spatial frequency information. We know this from the 60s and 70s and physiology, etc. So we know that this type of information is available earlier, and the idea here is that it's extracted very early, and in addition to this good old ventral pathway, there's a quick projection of low spatial frequencies that triggers this top-down facilitation of recognition, this top-down suggestion of predictions. So now we have a good hypothesis that this prefrontal activation that we found in the MRI experiment appeared early because it actually facilitates recognition. It's not just waiting for the result, and if you want to study early versus late, you can do this with MRI given the temporal resolution. So we had to resort to MEG, which I'm sure that most, if not all of you are familiar with. It's like EEG, but 10 times more expensive, and it studies magnetic field instead of the electrical field. But the idea here is really to see whether the activation that was early, and I see I don't have the movie here, but basically if you look at the time course, we've proved here in this MEG study that this prefrontal activation appeared 50 milliseconds before the temporal. Okay? So it does show that indeed earlier information in the prefrontal cortex is a real thing, and it doesn't show that it indeed supports the model necessary and it suggests predictions, but it does show that this activation starts early, which means it's in line with this idea. And there's a set of studies, and I won't be going through it, but there's 10 or 15 studies that support different aspects of this hypothesis that the prefrontal activation appears early, it's sensitive to the low spatial frequencies and to the number of candidates, and it sits nice with the idea that this prefrontal area actually facilitates recognition by generating early predictions. Okay, so moving along, we realized at some point that the more we looked at objects, that's not how we see objects in our environment. We don't see visual objects floating in space with nothing around them, right? With the more realistic ways, we see objects embedded with other objects, and they appear in typical scenes usually, and they are embedded with typical objects in typical arrangements. So there's some kind of probability assigned to everything here. So when you see a bed, maybe 90% of the cases you'll see a pillow, 70% you'll see this nightstand, 20% there'll be a carpet, but the brain has this, what we call statistical regularities, things that tend to occur in our environment with some regularity. The brain stores as association and then can generate as prediction with different level of confidence depending on this probability. So the idea here is really to look at context and to look at object association and how do they promote the generation of predictions and how do they promote our interaction with our environment. So we studied groups of individuals, this is with Lisa Eminoff, who is in New York now, studied how the brain reacts to objects that are highly associated with specific contexts and objects that are not associated with specific contexts. So when you look at a roulette wheel, you think casino, right? Every subject that we brought to the lab would think the same thing: casino, bowling alley, construction site, or these band village people if you're old enough. But basically you have a very limited set of contexts that are associated with each objects, and those objects that we equated with every dimension we could think of, but they are not associated with a specific context. And we identified this network, we call it with different names, contextual associations network, and you don't really need to memorize any of these names if you're not familiar with them, but the idea here is that we have this consistent and very vigorous and significant network, primarily medial surface, of areas that are activated when we see things that have high associations, high level of associations, high level of contextual kind of affiliation. And we started thinking about more and more about context and what we call context frames that capture environmental regularities that are learned with experience, both identities and relations. And they're activated rapidly by preliminary information in the image, and you can look also at examples with scenes, and these are examples from other people, Philip Shins from Glasgow, Odo Liva and Toralba from MIT, and you look at scenes just like I showed you the blurred objects, so also blurred scenes are highly informative. You look at it, it's like, this is garbage, why are you showing this to me? There's nothing here. And I say, you know what, hold on a second, just look at this blob here. What is this? And all of you, I think, see that this is a car, right? So in our everyday interaction, if you want to cross the road, you don't care what type of car it is. You just want to know that there is a car approaching. And that's as informative with context as it is with individual objects. And here, this is just an informal demonstration I created for a publication which showed that the same object can get different identity depending on the surrounding objects. We showed also with MAG, I won't get into this, that context is activated very early. So this network of contextual areas is activated very early. And we showed that, they facilitate recognition by generating predictions. So we show that contextual associations can create priming, can generate faster recognition compared with objects that do not have this association. So basically, this is just talking about, I just gave you a quick run through the idea that is not that new, that actually the brain has, relies heavily on associations to generate all this representation, and it's both, it makes for efficient memory representation, but it also makes very economical activations and helps us predict and be able to gain certainty in our noisy environment. So I'll just bring you back to the main hypothesis that I'm pushing here, and I'll start showing you some studies that talk about this more directly. So associative processing and the generation of, I'm sorry, just before I go back to this, hypothesis, I want to say something about this network. So I showed you this network of contextual association, this network that's active when we see things that are highly associative. And associative processing and the generation of predictions are integral process of default activity in the proactive brain. I talk about the proactive brain. It's the title of my talk, and the idea here is that the brain is not passive, but rather proactive. It, rather than sit there and be waiting to sensory information to stimulate representations and processes, it constantly tries to anticipate what's coming next. Even the most mundane thing, what is behind this door, what is going to be for lunch, whatever, right? So there's always some process that's going on that our brain is really never idle. And because, if generating predictions is a continuous proactive default operation of the brain, just like I said now, that the brain really always generates something, even we're in the shower, we're stuck in traffic or whatever, our brain always makes some plans, some what-if simulations. We always generate something about the future. And it relies on associative activation. Then one needs to show that associative activation is a continuous default process in human thought. This is kind of a convoluted way of saying that if we're constantly generating predictions, and if predictions rely on associations, can we see that the brain is constantly activating these associative areas? And indeed, we showed here that if you're familiar with the default network, this area of the brain that's active when we're not doing anything specific, when we're not consumed by a specific demanding task, there is this vigorous network that's active, and we found this remarkable overlap between the default network and contextual association network. So really saying that what we do when we're not doing anything is generating predictions that are based on associations. Okay, back to our main business here. So a quick first pass of rudimentary information determines our impressions, guides our predictions, and shapes our perception. So I showed it to you to some extent. Nothing is, it's not math, so it's not fully proven, but I showed you suggested evidence to support this idea that low spatial frequency objects and also with scenes are enough to kind of give us the kickstart for recognizing, for triggering, for interacting with our environment. Let's look at other domains. And one domain I would like to consider here is that of social interactions and judging other people based on their looks. So we look at these objects here, or these faces here, and the studies that we did here was actually initially, I was curious about what is the visual information in a face that determines our impression of that person. We all know that we all seen in kind of jumping to conclusion. We see somebody new and we think this somebody is generous or is smart or is cool or is a leader, is weak or whatever, right? So we jump to conclusions. We don't act on them, hopefully, but our brain has the arrogance of jumping to conclusion because that's an ingrained capability. Just like we do it with a baby chair that I showed you, just like we do with objects, our brain extends this ability also to humans, which even though it's less desirable, it's there. So the question was really what type of information guides the formation of our impression, and this is very quick impression. In fact, so quick that we kept lowering the exposure duration. We made it faster and faster until we reach this lower limit, and we found that people at 39 milliseconds is enough for people to reach consensus. I don't know these people, and I don't know if they're really threatening or not in terms of their personality, so these are all stimuli, and we actually didn't ask threatening, but really trustworthiness, which is kind of parallel. But these are just our top rated people, and I don't know them, and I don't want to meet them, but I don't really know if they are threatening in reality. But the thing is that even 39 milliseconds, extremely fast, 39 millisecond exposure was enough for the vast majority of our subject to reach a conclusion or to reach a consensus. These guys are, and there's a whole, David, you want to do it now? Okay, go for it.
Was this mask paradigm?
Yes. Yes, it's mask, yeah. Without, as David alludes to, without a mask, you can present something for 1 millisecond. If you don't put a mask, it feels like forever. So we do this picture, and actually I ran through this, but here's the mask. You see just behind each face there's a mask. So this is kind of outrageous that 39 milliseconds, the early information that we extract, 39 milliseconds is enough for people to say, oh, this guy looks intelligent, this guy looks threatening, and so forth. But, we're not here to change the world. That was, in that sense at least, to educate society about first impressions, but rather to understand, okay, we reached a limit of 39 milliseconds. Let's see what is the information in these faces that really guided this formation of impressions. And we filtered the faces to low spatial and high spatial frequencies. And we found that actually, well, I don't show it here, but basically the same consensus was achieved in the low spatial frequency, but not in the high spatial frequency. Meaning that this quick judgment of other people, these quick impressions are there and are existent when we look at the low spatial frequency. The information that's available early on, this is what determines whether we think somebody is X or Y, okay? So, first impressions we know are quick. We know that, unfortunately, are also lasting impressions. But the idea here is just like with objects that I showed you, the low spatial frequency kind of generate the predictions of what to expect from this object. Here we do the same thing. We extract low spatial frequencies very early, and we use them to guide our interactions with these people. Okay, so I'll jump through this text. I think it's the last study I want to mention is, and Robert, I think yesterday, I know, referred to this finding of ours. The idea is really that to look at preference of people between for curved versus sharp objects. And these are, of course, extremes. We look at the first hypothesis here that we said was people would like sharp-angled objects less than objects with curved contour. And the idea here was really to use real-world objects, neutral objects, emotionally neutral objects. So we all know that people would love more, rounded kittens or teddy bears more than broken glass and knives, right? This is not something to write home about. But what if I take these objects and we manipulate them and we create pairs of everyday objects that don't have any deep emotional valence to them, and you can see these cell phones and you understand how old this study is. But the idea here was really to look at objects that we can make as comparable as possible, and just the only difference was the shape of their contour. And let's leave this for now. So we created a lot of pairs of everyday objects. We also, just to control for semantics, I didn't think we really needed it, but just to make it more complete, we also created meaningless objects that are more comparable, more controlled, and we found the sharp and the smooth versions of the same objects. And we also had these mixed objects that had both sharp and smooth. And we found that people liked the curved objects more than the sharp objects, and the mixed ones were conveniently in between. It's all significant. And I thought it was very exciting because these are objects, it's just wristwatch. You just show people wristwatch, and they like this one better than this. Consistently, they like the ones with the smooth contour. Just on a side note, anecdote, this paper found its way to the famed architect Frank Gehry, and he gave a talk in front of, the Neuroscience Society has this big meeting, 20, 30,000 people, and the first one, at the first day, they have a Science Society speaker. The first speaker was Dalai Lama. The year after, it was Frank Gehry. And luckily, I wasn't there in this talk, but he referred to this paper, and he said, and I think it's very relevant to this meeting, that's why I'm mentioning it, not just name dropping, but he said something like, don't you scientists tell us what's beautiful and what's not beautiful, right? So if people like this, it doesn't mean that I'm going to, I think Frank Gehry's buildings are more like this mixed design there, but basically it's a good anecdote to help me remember to tell you that we're not claiming that the single, that I don't think anybody here believes that there's a single rule of how to make things beautiful. Okay, make the whole world curved and everything will be beautiful. It's only one dimension, one factor that affects, and we all, I think, like many objects that are not smooth, and there are other things that are affect the way we like things. And you just mentioned to me when we talked about what you studying, how people like scary things or negative things, right? So we sometimes, that was how you said it? Yeah, roughly, okay. So we know that sometimes people like things that even if they're not pleasing or make us feel most comfortable. And of course, there's cultural differences and etc. But just kind of speculative aspect, but I have the slide here. I'm not big on evolutionary psychology, kind of trying to find the real source of why we like smooth over sharp angles, contours. But we did run this, we had an MRI machine close by, so we ran this experiment, and the hypothesis here was that the sharp objects would activate the amygdala more, just because we thought there's some kind of inner fear that is associated with seeing the sharp angles, okay? And indeed, we found increased activation in the amygdala. It's hard to see here, but it is there and it's significant, and it was published, that this is work with Meital Netta, I didn't mention here, but she's now a faculty in, I don't remember where, but in the US somewhere. I don't remember where. Anyway, so the idea here, I think that regardless of the explanation and regardless of how seriously we take this evolutionary aspect, like, sharp objects, even if it's neutral objects, if they have sharp contour, they remind us something scary or whatever. But the fact is that everyday objects with sharp contour activated the amygdala to a higher extent than the smooth objects. So even, we don't have to use these scary IAPS images, if you know them, or scary images of dogs and weapon or whatever to activate the amygdala. It's enough to just use everyday objects if you control for the contour. And here again, we wanted to see what drives our preference for the curved versus sharp objects, and we filter. That's our preferred manipulation in the lab. We filter those objects to low spatial and high spatial frequency pairs. And you have to know that there's, technical details I'm skipping here, but you have to understand that we control for, like if you filter, you can filter to different extent. You want to make sure that they are equally recognizable in terms of difficulty. So we control a lot of things before we do manipulations such as this. It's not just capricious filtering here, but once we filter and we equate everything, we find that only or mainly in the low spatial frequency, we maintain this preference for the curved, but not in the high spatial frequency. Again, suggesting that this coarse information that's extracted early is what determines, in this case, our preference towards objects. Before that, I showed it to for faces and first impressions, and before that, for objects and scene. And I think you're all familiar with these old demonstrations that people can associate different sounds with different shapes without further instruction. You just ask them to say which one is the kiki and which one is the booba, and everybody knows which is which. So we do have this ingrained affiliation with smooth and sharp. We have, there's a bunch of follow-ups to these studies of curved, and you heard a little bit already, and Helmut, I don't think we'll be talking about this today, but we do have a follow-up that he was generous enough to include me in, that also did the emotional aspect of this preference. With some side projects we have in the lab, we collaborate with architects that came to us after they heard about this finding and said, okay, let's generate spaces in virtual reality, and now they do it in real reality, and generate these spaces and see how do they affect the feeling of people inside those spaces if they make the space curved versus sharp, and so on. And this is just, it's published, but this is too detailed here. There's no bottom line I can tell you. Other than, by the way, I gave this talk about the curved when it came out, I don't know, 2000-something. I was back in Boston back then, and I gave this talk in the Harvard Graduate School of Design. It's the architects and the artists and the designers. And they all came to me after the talk. It's like, what are you talking about? We like the sharp objects more than we like the curved objects. So there is some bias here between people. I think that, you know, curved objects for me is like this dinner I saw yesterday with mashed potatoes, sauerkraut, and a big sausage. You know, there's a comfort food in the US. This is curved contour. It makes you feel comfortable. It makes you feel unintimidated, but it's not the extreme. And I think that that wasn't scientific what I just told you about the mashed potatoes. It was a metaphor. But the idea here is indeed that there's the easy way to feel comfortable and to feel beauty, but I don't think it's the only one. Okay, so I'm going to wrap up by saying that, just reminding you again that the lasting primacy hypothesis, that a quick first pass of rudimentary information determines our impressions, I showed you with objects, with faces, with first impressions, guides our predictions, and shapes our perceptions and preferences. I think I'll just stop here, or maybe I'll just stop here. I'll leave you with the conclusions. Just before that, I'll say thanks to the different generations of lab members that helped with this, but thank you very much for your attention.